I know it's gonna be tough, but we got this.
I'll solve all your problems.
What?
Here, let me help you get the reality stone.
Okay.
What could that possibly be?
We must solve this problem, but now we have the math whiz to guide us on our journey.
So for this problem, we're trying to approximate the area under the curve from -2 to 4. Before we create the rectangles, we need to figure out how wide each rectangle will be. To do this, we need to figure out the width, delta x. In the formula, a is the lower bound, b is the upper bound, and n is the number of intervals of the integral area we are approximating. So that gives us delta x is equal to 4 minus -2 divided by 3, which equals 2. Each rectangle has a width of 2 then.
Okay, I think I understand the width part now, but how do we actually make the rectangles?
Now that we know each rectangle has a width of 2, we can split the interval into 3 sub-intervals. So our intervals are from -2 to 0, from 0 to 2, and from 2 to 4. Since this is a left Riemann sum problem, we use the left endpoints of each interval to determine the heights of each rectangle. That means our rectangle heights come from f of -2, f of 0, and f of 2.
So for a left Riemann sum, the left side of each subinterval determines the height of the rectangle?
Exactly. We only use the left side to calculate the heights. Each rectangle's area is width times height. Since every rectangle has a width of 2, we multiply 2 by each function value and add them together. So our approximation becomes 2 times f of -2 plus f of 0 plus f of 2, which is 2 parentheses 6 plus 2 plus 6. So the estimate of total area under the curve is 28 units squared by LRAM.
This kind of makes sense now.
I think this is for you. Let's make our journey to the next step.
What are you doing? You know what understanding Riemann sums will do to the world.
You can't stop us now. We can't fall this way.
Oh no, not another one.
Okay, so you guys understand left Riemann sums. So right Riemann sums are the same, except we are using the right heights.
Okay, since this is the same graph as the question we did the left Riemann sums, we know the interval goes from -2 to 4, and that there are 3 equal subintervals. First, we calculate delta x to find the width of each rectangle using the formula delta x is equal to b minus a over n. Since this is the same graph as before, a equals -2, b equals 4, and n equals 3. So delta x equals 4 minus -2 over 3, which is ultimately equal to 2. That means each rectangle has a width of 2 units, and our subintervals are from -2 to 0, and from 0 to 2, and from 2 to 4.
Wait, is that not the same thing we did for the left Riemann sums? So what actually changes?
The only differences are which endpoints we use for heights. Since this is a right Riemann sums, we use the right endpoints of each subinterval instead of the left. So our rectangle heights come from f of 0, f of 2, and f of 4, because those are the points on the right side of each interval. Since every rectangle has a width of 2, we multiply 2 by each function value and add them together. So our approximation becomes 2 times f of 0 plus f of 2 plus f of 4, which is 2 times 2 plus 6 plus 18. So the estimate of the total area under the curve equals 52 units squared. That's it. That's how you solve it. You're always my favorite daughter. I always tried to get Nebula to be better at math. I even put robot parts in it. He's my favorite. This is goodbye.
She didn't stand a chance. I heard what you did to your daughter. Newsflash, he had to do that, and you're next.
Okay, we'll try and solve this one.
Okay, this question is a bit harder. This question is asking us to use trapezoid sums, so we have to use a different method. Instead of approximating the area with rectangles, we are approximating it using trapezoids. The formula of this one is A equals 1/2 height parentheses B1 plus B2. In this formula, h represents the distance between the two bases, which is our delta x, and B1 and B2 are the heights for the graph at the endpoints of each subinterval.
Okay, so first we find delta x, which is the same as the previous questions, as this is the same graph. So delta x equals 6 minus 2 over 3, which equals 2. That makes our intervals -2 to 0, 0 to 2, and 2 to 4.
Perfect. You guys are getting the hang of it. Now calculate each trapezoid separately.
For the first trapezoid, the bases are B1 equals f of -2 is equal to 6, and B2 equals f of 0 equals 2. And the height is 2. So T1 equals 1/2 times 2 times 2 plus 6 is equal to 8.
For the second trapezoid, the bases are B1 equals f of 0, which equals 2, and B2 equals f of 2, which equals 6. So T2 equals 1/2 times 2 times 2 plus 6, which equals 8.
The last trapezoid bases are B1 equals f of 2 equals 6, and B2 equals f of 4 equals 18. T3 equals 1/2 times 2 times 6 plus 18, which is equal to 24. So now we add all three trapezoid areas together. T1 plus T2 plus T3, which is 8 plus 8 plus 24, equals 40 units squared.
You must have known this was going to happen.
Yeah, you guys are just too good at Riemann sums.
This is where my journey with you guys ends. Complete the mission and get the Yellowstone from Anna's head.
Don't have your little helper, do you?
You know, I may not, but I have Lakshanya by my side. What is this?
Don't worry, I can do this. Okay, for left and Riemann sums, we need to look at whether the function is increasing or decreasing. We can tell that by looking at the slope, f prime of x. That means if the function is decreasing, the left Riemann sum overestimates the actual area because the left endpoints of each subinterval are higher than the original graph. So the rule would be the opposite for when it is increasing, meaning that it would be an under-approximate.
So, what about for right Riemann sums?
You use the same logic for right Riemann sums. However, the rules are switched. The right Riemann sum over-approximates the value of the definite integral when f of prime is greater than 0. The right Riemann sum under-approximates the value of the definite integral when f prime is less than 0.
Okay, that makes more sense, but what about for trapezoidal sums?
For trapezoidal sums, we don't see whether the function is increasing or decreasing. Instead, we look at concavity, which comes from the second derivative f double prime of x. If the graph is concave up, meaning if f double prime is greater than 0, the trapezoid lies above the curve, so the area. But if the graph is concave down, meaning if f double prime is less than 0, the trapezoids fall below the curve, so the trapezoidal sum underestimates the area.
Where did you pull that knowledge from?
I had a great teacher.
Now is finally the time. What the?
I'm the true calculus teacher.
All right, guys, today we're going to learn about something called Riemann sums.